Welcome to this module focusing on derivatives. We will delve into three essential topics: Rolle's theorem, the mean value theorem, and the intricacies of deriving implicit functions. The prerequisites are a familiarity with elementary functions and a rudimentary knowledge of basic mathematics. I believe the examples we'll present today won't be overly challenging. Rolle's theorem, what does it convey? Let's start by assuming that f represents a continuous function. What does continuity entail? In a simple sense, continuity implies that we can depict this function without ever having to lift the pen from the paper. And it is defined in a certain closed interval, a, b, which can be minus 3, 3, minus 1, 1, or 0, 1, whatever you want. Furthermore, for the function to meet the conditions of Rolle's theorem, it should be differentiable throughout the entire interval, with derivatives at all points within that range. When we examine the function at points a and b, this signifies that it starts and ends at the same height on the y-axis, allowing for any continuous behavior in between as long as it adheres to the continuity criteria. As per Rolle's theorem, there exists a point c within the interval between a and b, where the derivative is equal to 0. Let's take a look on how does this concept work. The question is, what does it mean when the derivative at point c is 0? To put it simply, if we revisit the basics, the derivative at c represents the slope of the tangent line. The notion that we can identify a point where the tangent line has a slope of 0 indicates that the tangent line is horizontal at that point. In other words, we can always find a point where the tangent line is perfectly level. It's worth noting that this holds true even when the function f is constant, resulting in a flat function with a slope of 0 for every point. Let's examine an example to understand it better. I've plotted a parabola, specifically the function minus x squared plus 4, within the closed interval from minus 2 to 2. From the graph, it's evident that this function is perfectly continuous, meaning we can draw it without lifting the pen from the paper. Now, according to Rolle's theorem, there exists a point. In this case, it's straightforward to find it 0, where the derivative is exactly 0. This implies that the tangent line at that point is completely horizontal, a characteristic clearly visible in the tangent lines, as I hope you can observe here. An essential point to note is that Rolle's theorem assures us of the existence of such a point, but it doesn't provide a method for calculating the specific location of that point. Another equally vital theorem worth mentioning is the mean value theorem. Notice that it bears a resemblance to Rolle's theorem. The mean value theorem stipulates that we have a function that is continuous within a closed interval a to b, just as in Rolle's theorem, and it is differentiable within the open interval a to b. So, it maintains the same continuity criteria where you can represent the function without lifting the pen from the paper. Additionally, we can calculate the derivative of that function at all points within the open interval, excluding the endpoints. Let's consider an enhancement to this theorem. What has been altered is the removal of a prior condition, the requirement that the function at a must be equal to the function at b, meaning that it starts and ends at the same level. Can we still guarantee the same outcome as before? The answer is no, we can't. However, what we can affirm is the existence of a value c, where this equality holds true. The derivative at c equals f at b minus f at a, divided by b minus a. This statement has multiple interpretations, so let's explore one of them. As we've discussed tangent lines and secant lines in previous videos, now is the perfect moment to apply this terminology. Let's see, I remind you. The right side of this equation corresponds precisely to the slope of the secant line that connects the points a, f of a, and b, f of b. In other words, it represents the slope of the line passing through the initial and end points. The secant line, depicted here in a greenish color, is visible below. This would be the secant line connecting a, f of a, and b, f of b. The interval here is approximately 0.4 and 2 to provide a rough idea. The slope of this secant line corresponds to the expression mentioned. You can deduce this by straightforwardly calculating the slope of the line connecting 2 points. What the mean value theorem assures us is that I can pinpoint a point c, highlighted in bold here, in a manner such that the slope of the tangent line, indicated by this line, is precisely identical to the slope of the secant line. In essence, it means that the tangent and the secant share the same slope. Alternatively, you can express it as the derivative at c equating to the slope of the secant line. That's the essence of what the mean value theorem conveys. It applies in many situations, but, as mentioned earlier, it is primarily an existence theorem. Its role is to ensure the presence of a point that fulfills this condition, without providing a method for pinpointing that point. It leaves the task of determining that point to us. Now, let's explore another vital theorem that hasn't been discussed yet, but is frequently applicable. This theorem states the following. Any function that is differentiable at a specific point, denoted as x sub 0, is also continuous at that point. Differentiability implies continuity, but the reverse isn't necessarily valid. Pay close attention, as this is what we'll examine now. For instance, consider the function f of x equal to the absolute value of x, which is continuous at x equals 0 but lacks differentiability. What does the graphical representation of this function look like? It's the graph with this peak right here. As a reminder, the modulus of x behaves as x when x is positive and as minus x when x is negative. Why do we define it in such a peculiar way? It may seem unusual. When x is positive, we simply leave it as is. That's what I mean. However, when x is negative, such as when you have a value like minus 3, how do you calculate its modulus? You essentially remove the negative, but conceptually, we add an additional negative sign, turning minus into plus, effectively making it positive. This function is continuous. We can represent it without lifting the pen from the paper. However, at the point 0, it lacks differentiability. When applying the definition of differentiability, we observe that it yields one outcome on one side and a different outcome on the other. The tangent lines do not coincide on both sides of the point, which is why it's not differentiable at that particular location. This example demonstrates that some functions are continuous but not differentiable. In contrast, the theorem states that if a function is differentiable, it is definitely continuous. This implies that differentiability ensures smoothness and prevents the occurrence of such abrupt peaks. In the final segment of this video, we'll delve into implicit differentiation. Frequently, we encounter scenarios in which we cannot explicitly differentiate a function using our standard methods. In such cases, we require a technique to address these problems. Let's proceed step by step and understand the nature of such problems. If we're given an equation in the form y equals 3x cubed plus 2, I would interpret it as follows. That y is a function of x, where x serves as the independent variable, and the value of y depends on the value of x. The variable x determines the value of y, making y the dependent variable. In this case, deriving is quite straightforward. We can simply express y prime as equal to 9x squared since the constant 2 vanishes when we differentiate. But what do we do when the function is not provided explicitly, meaning one variable isn't expressed as a function of the other, as in the previous example? In such cases, we encounter equations like the following simple one I've presented. X times y equals 1. Here, there isn't a single variable that's explicitly isolated. It's just an equation stating that x times y equals 1. This equation implicitly defines another equation, y equals 1 over x, within the appropriate domain. It's important to note that this function is not defined at 0, so we would need to specify the domain in which this can be evaluated. But this goes beyond what we're covering today. We're dealing with a basic equation here. By rearranging it, we end up with another equation like this. What I'm highlighting here is fundamental. We're expressing y as a function of x. We could have solved for x and defined it as a function of y, saying that x is equal to 1 divided by y within the suitable domain. However, we've opted to represent it as y being a function of x. If we're asked to find the derivative of the equation x times y equals 1 with respect to x considering y as a function of x, the most straightforward steps would be as follows. Begin by isolating y from the equation as we've done previously, resulting in y equals 1 divided by x. Express this explicitly and then differentiate with respect to x. This process yields y prime, the derivative of y, which is the derivative of 1 divided by x. This differentiation step is quite simple, and I encourage you to practice it. The result, which I'll share with you, is minus 1 divided by x squared. In essence, the derivative of 1 over x is minus 1 over x squared. And what if it is not even possible to begin with the first step, which is to isolate y from the equation? In such cases, we would need to employ a technique known as implicit differentiation. The process involves the following concept. The idea is, and I believe I haven't emphasized this enough, that even if we can't explicitly isolate y, we still treat y as a function of x. we could approach it the other way around. But for now, let's consider y as a function of x, which we haven't isolated. Nevertheless, it's important to remember that y still relies on x, a crucial point to consider during the differentiation process. Our approach involves differentiating both sides of the equation with respect to x. This is quite straightforward. Whenever there's an x term, we differentiate it as usual. However, every time we encounter a y term, we add y prime because we are considering y as a function of x. This is a critical concept, similar to when we previously expressed y as 1 divided by x, acknowledging that y is a function of x. In this case, even though it's not explicitly shown, we are assuming that y is a function of x within a suitable domain. So, as I reiterate, when we differentiate both sides of the equation, and for every occurrence of y, we include y prime of x applying the chain rule. What's our next step? We gather all the terms that involve y prime of x on the left side. The choice of left or right side is purely a matter of notation, and you can use either side of the equation as you prefer. Next, we factor out the common factor from y prime, and as a final step, we isolate it. Let's see an example because it becomes much clearer through examples. Imagine we have this equation, y cubed plus y squared minus 5, y minus x squared equals minus 4. Now I ask you to find the derivative with respect to x considering y as a function of x. Someone needs to specify this because it's also possible to treat x as a function of y. In that case, the approach would be simpler, as we would transfer all of this to the other side, resulting in two functions, including the square root. However, we won't delve into that alternative approach at the moment. The point here is that we're dealing with this equation, and our goal is to find its derivative with respect to x. Let me emphasize, we're treating the function in terms of x as a function of x. The initial step is to differentiate both sides of the equation with respect to x. Let's simplify this a little. The derivative of 4 is clearly 0. The derivative of minus x squared, I trust you're familiar with this, is minus 2x. Let's proceed with differentiation. The derivative of 5y, and here's an important point to consider, is that since y is a function of x, we simply write y prime. We differentiate the function y with respect to x, and because we may not know the exact form of that function, we denote it as y prime. Now, how do we differentiate y squared? Well, this involves a composition of functions, where y depends on x squared. As you might recall, when you differentiate y squared, you bring down the exponent 2, subtract 1 from it, and also multiply by the derivative of the inner function. Now, the derivative of this inner function, which is y, is something we may not know explicitly. So again, we represent it as y prime. Now let's move on to differentiating y cubed. The 3 exponent comes down, 1 is subtracted from it, and once again, we apply the chain rule where the derivative of y, represented as y prime, is involved. It's essential to understand that every time y appears, we differentiate it just as we would an x, with the added notation of y prime at the end. This notation is key in these steps. What follows is relatively straightforward. This was the most complex step and can be a bit confusing. Now, we group all the terms that contain y prime. Notice that there are y prime terms here, here, and here, all adding together. Also, note that I've moved the minus 2x to the other side. We are essentially grouping more terms. Now, with all the terms containing y prime, we factor out this common factor. I'm left with 3y squared plus 2y minus 5 equals 2x. What's the next step? It involves isolating y prime, which essentially means moving all these terms to the other side of the equation by division. Of course, this is valid as long as we are operating within the appropriate domain. So, here we have successfully found the derivative of the function y with respect to x from an equation where y was implicit and not explicit. I hope you found this information helpful. Today, we covered Rolle's theorem, the mean value theorem, and implicit function differentiation. If you have questions, please feel free to ask in the forum. Thank you for your attention.